Thank you very much for the invitation. It's a pleasure to give a talk here. I'm Danai Koutra. I'm an assistant professor here at Michigan in the Computer Science and Engineering department, and I lead the Graph Exploration and Mining at Scale group. So the talk that I will give will be quite different from the one we just heard, and I will focus more on the mining side. What can we do with the data that we have? So there's no question that we are generating a lot of data every day, right? Each person alone is generating a lot of data. Companies are collecting a lot of data. And the cool thing about this is that a lot of it is often interconnected. We don't act in isolation, but we are interacting with each other, right? And this can be naturally captured within a graph or a network. So a graph consists of nodes and edges. The nodes could be entities, let's say users, and the edges could be connections between them, some type of relationship, such as friendship. So networks are everywhere, right? From traveling around the world or capturing facts about the world in knowledge graphs, or in social media where we're interacting with each other. And a challenging thing about these networks, and I know this is not a big data conference, but a challenge with that is their size. They can have millions or even billions of nodes and interactions between them. So we really need computational methods that can scale up to those. And I argue that they also call for summarization techniques. So that we can compress, we can represent the data with a much, much smaller graph, a much smaller network that we can operate on much faster. And we can also gain insights into those. So in my group, we do a lot of work around summarization. But in this talk, I will focus specifically on representation learning. And there was a quick mention to embeddings before, so I'll talk a lot more about embeddings now. Now, since I'm the first one really going into details for this, I want to give you the goal of representation learning, which is, in the case of graphs, given a graph, we want to learn a feature representation for each node automatically. So instead of extracting from our data things that we understand over time spans and so on, we want to learn what is the right representation. So at the end, we come up with a vector that captures some properties for the nodes in the network. So in data mining, there's a ton of work on network representation learning. Actually, in the last 3 years, there are over 100 papers. Actually, there are more. This is a repository that keeps track of all the papers that is worth reading in this area. So it is very fast pacing, and then there's also a lot of interest in symposiums and workshops and tutorials just on this topic. But if I were to summarize in one sentence, what a lot of the work does is that they focus on preserving proximity between nodes. So the idea is that if two nodes are close to each other in the graph, then they should be embedded closely in the latent space, right? So these vectors should preserve that similarity in the original graph. And there are a lot of tasks that we can do based on these. We can perform link prediction, classification within a network, clustering, and many other tasks like cohort identification and so on. However, I will argue that sometimes structural similarity is more important than proximity. Right? And there are tasks that need structural similarity that involve multiple networks. For instance, I need to learn representations that can generalize across networks. I cannot just preserve similarity within a network alone. And this comes up in alignment. Actually, a student of mine, Mark Hyman, is going to give a talk about this later today in graph similarity and classification and many other tasks. And even within a single network, sometimes structural similarity is more important. And this comes up in classification, in anomaly detection, in role discovery, and more. And I'll give you some examples later on. So, given that everyone is studying embeddings these days, there's no doubt that they're very powerful. But one thing that is negative about them is that they can take up a lot of space. So the original graph, or the adjacency matrix that represents a graph, is really, really sparse. And we can use that fact in order to speed up computations. However, the embeddings that we learn, which are just n vectors of whatever length, they are super dense and they're real valued numbers. So even if we have a billion nodes in a graph and we use the traditional embedding length, which is 128, then we need about a terabyte to store this, right? And then every time we need to operate on this and make inference, we need to read all of that data and continue with other tasks. So the question that we were interested in is, hey, can we do something to summarize those? Can we come up with a latent network representation that we can use instead? So the problem that we are solving is the following. Given a graph, which can be arbitrary, we want to find a compressed representation that maintains some structural properties of this graph. And it needs to be independent of the graph size. So I don't want to be learning a vector per node, for instance, as we do typically. And I should be capable of deriving node representations from that, right? So that I can perform downstream tasks. And other desired properties, as I said, we want to be able to handle arbitrary graphs. We want high compression rate. We want it to be inductive, so we can learn the summary on one graph and apply it on another one. And also, we should be computing embeddings on the fly. We should be able to do that. So I'm not listing 112 papers here, but the main difference between the work that exists, either in graph summarization or embeddings, is that all of it is size dependent. So the summaries that we learn depend on the size of the network. And this is the main difference in the work that we look into. So before I go into the details for this, I'll give you the overview, the key elements of the approach that we have. So imagine we have this input network. There are different object types, for instance, different websites or resources that the user accesses. And the first key element is to use relational functions in order to capture some structural features in the network. Somehow we need to represent the nodes. So I'll refer to that as the recipe, essentially. I'm giving you what you should be using in order to get the structure of the network. Then the second key element is to represent context in terms of histograms. And in representation learning or embeddings, finding the context is one of the key steps in finding eventually the representations of the nodes. And then the last thing which allows us to have a compact representation is to find the subspace vectors from which we can derive the embeddings. Okay? So these are the three key elements, and I'll be coming back to these as I go through the approach in more detail. So the approach that we have is called multi-lens, and as I said, it starts with using relational functions. So the idea is we start with some graph functions, such as just summation. That could be a very simple one, that operates on a subgraph in the network. One common thing that we do is we focus on egonets, the network around a specific node, the network as a node plus its one-hop neighbors. So in this case, if I were to apply summation, and then I restrict it on different directionality for the edges, I could get the in degree, the out degree, and the total degree of a node. Okay? Again, I'm capturing some structural properties. Now, I don't want to just do that, right? This goes back to feature engineering, essentially. I'm deciding what to extract. So we want to be able to learn some new features, and ideally non-linear ones. So what we do is we recursively apply graph operators in the neighborhoods that we have defined. And some operators that we look at is max, min, summation, mean, variance, and others. Now, the way that you can think of it is that compositions over a node's neighborhood is equivalent to capturing higher order structural features in L-hop neighborhoods. Right? So if I compose max twice, it's almost like I'm operating on the two-hop neighborhood. So the next thing, which is, again, a key element of representation learning, is to define the context of a node. And the way in order to find the structural identity. So what we do is we use histograms. And because we are using structural features for the nodes, and we know that these are very skewed in large networks, we use log scale for that. So for instance, for this red node at the bottom, we find the feature distribution in its neighborhood, let's say for the first feature. So that will be the first row that I have annotated with red. For the second feature, we can get, again, the distribution, and we concatenate those. The nice thing about histograms is that they are very flexible. So they can easily incorporate node types, edge types, directionality, and so on. All we need to do is restrict the neighborhoods to different types of nodes and edges. For instance, here, there will be an animation. I could focus only on nodes of this type or this type, and then concatenate the histograms. So it is very, very flexible. Now, the last part is to actually find a summary, right? Because so far, we have representations for each node. How do we find the summary? There are a lot of different ways, but here we resort to matrix factorization, which is shown to be essentially the technique that, or a lot of embedding techniques that exist out there are equivalent to performing matrix factorization on some similarity matrix. So we built on that idea here. And the summary, if we were to use SVD, for instance, for matrix factorization, the summary would be the second part of SVD, which is independent of the number of nodes. It just has to do with the dimensionality that we want the embeddings to be. So to summarize, we follow a whole process, but then we don't need to store anything in between. The summary that we need to store is just those low-rank latent graph summaries, the latent space, essentially, the subspace that we found, and the relational functions, the recipe to get to that point. One nice thing about this is that we are capturing structural properties. These generalize across networks. So we can train potentially on small networks and apply it on larger ones. And we are also using a technique that is independent of the node IDs, which again generalizes. And another nice property of this is that we can, because of that, actually, because of the fact that we can generalize, we can learn a summary on one graph and now apply it on another one and find embeddings in a new network. So I started this with, hey, we need to summarize. So the first result that I want to show you is the space comparison between our approach and traditional embedding approaches or graph summarization techniques. So I'm showing you for different data sets, and you can see the size here. So they go up to about 4 or 5 million edges. And I'll show you, I'm also showing you how much space multi-lens takes in megabytes, the summaries. And now after I click, you'll see how much more space each other technique that we have needs. So in summary, they need about 79 to 2100 times more space in order to store these real valued representations for all the nodes. Right? So we have huge savings in space. Now, space is not the only thing that matters, right? We want to be able to use the representations for other tasks as well. So what we looked at is link prediction, which is a traditional task that all embedding techniques look into. So I have, with gray over here, some techniques that are just graph summarization. They summarize the graph in the original space by grouping them together, by grouping nodes together. I'm giving you some techniques that that operate on homogeneous graphs, let's say a graph of users and their friendships. Then 2 approaches for heterogeneous graphs. Let's say I have users accessing websites and other resources, so a lot of different types of nodes. And traditional graph convolutional networks and other deep learning techniques. So the takeaway here is that our approach, multi-lens, outperforms all of these techniques from 1% to 88%. I mean, there are some techniques that lead to very, very low accuracy. And another thing to note is that a lot of them run out of memory. We have 16 gigabytes that we're using in here for RAM, or they run out of time. And we give 24 hours to perform the link prediction task in this case. So a lot of the techniques that are powerful in much smaller graphs, like the GCNs, the graph convolutional networks, they are not able to scale to the graphs that we are looking at here, which are not massive. They're good size, if you ask me. So the other thing that we wanted to look at is other types of applications. Like often we care about anomaly detection. We want to find when there are significant changes, let's say in a computer network, so that we can flag that, hey, something is happening. We can use these summaries that we learn to perform this task. And what we do is we learn a summary at one timestamp, and we use it, we apply it to the next timestamp. And then we compute the distances between the embeddings of the nodes in these two. If the distance is very high, then it means that something has changed significantly in the network. So we applied this to different types of networks, including a Twitter data set. And there what we had is hashtags as nodes, and then if they co-occurred in some tweet, they were connected with each other. And this spans from May to July 2014. So what I'm showing you here is the distance between consecutive timestamps. So each point compares the timestamp before and let's say t-1 with t. And by using moving average and finding distances that are more than 3 standard deviations away from the median, we're able to find some events. And these correspond, for instance, to the Gaza-Israel conflict or the Ebola virus outbreak, events that really changed the way that the hashtags were connected. Now, we also applied this to NRUN. This is a favorite data set in data mining. We all apply things on NRUN, and we all find the same things again and again. So this is just proof of concept that, yes, indeed, we can also find important events in NRUN's history, such as Skilling. In one of these events, Skilling resigned. In another one, Baxter and a vice chairman of NRUN committed suicide. So there are some events that cause changes in the structure and in the way that people communicate. The other thing that we care about is scalability. We want to make sure that whatever technique we have can scale to large networks. So in this case, we experimented with networks up to 10 million nodes and about 100 million edges. And here we compare it to node-to-vec, one approach that is commonly used for embeddings in graphs. And it is pitched as very scalable. So in this case, you see that node-to-vec runs out of memory at about 1 million nodes. But with our approach, we can get more scalability in this case. So this was one example of work that we have where we care about embeddings and summarizing somehow the embeddings. We also have some ongoing work on finding embeddings that are binary. So instead of having real valued embeddings, if we go to a binary format, then we know we have techniques to save space and operate over these sparser representations quickly. So that was the approach that we took in another project where we cared about user stitching. So imagine that we have users using multiple devices and we want to provide the seamless experience across all of those devices, right? So there are different IPs and different characteristics there. So I'll just give you the key ideas behind this approach. I'm not going to go into details. The ideas is, one, we want to take into account the temporal aspect. Interactions are changing over time, so we want to incorporate that in the embeddings that we learn. The other thing is, instead of using relational functions, which we did in the previous work, we said, okay, let's use random walks, which is a powerful tool for embeddings, for learning embeddings over networks. But now, because still we want to learn the structure and we still want to be able to generalize, we'll apply walks and these will sample features, attributes, things that can generalize as opposed to IDs that are unique to a specific graph. As before, we use histograms, and actually we've used that in several different projects, and we've seen that they're very powerful in capturing the context. And then the last part is to use some hashing so that we learn embeddings that are binary and save up a lot of space. So just one result here. Again, we compared to several different techniques for heterogeneous and homogeneous graphs, and we see that that approach also can lead to 96,116 times less space for the embeddings. While we still get very good accuracy in various downstream tasks. So to conclude and share with you some takeaway messages, structural embeddings in networks are way less studied than proximity-based embeddings, but I argue that there are a lot of applications and a lot of tasks where structure is more important than proximity. Summarization is a great tool if we want space efficiency, and in this work we combined graph summarization, which operates in the original domain in the original space, and node embeddings. Histograms are quite powerful in capturing the graph structure. They are flexible and versatile. We can incorporate attributes, directionality, weights, whatever you want to encode in a graph, so it can be a really complex graph. And they do lead to less information loss. Right? It's better than saying, okay, I'll pick the max or do max pooling or mean pooling and so on. And scalability is necessary in order to make sure that we can apply techniques to large graphs. So ideally, we want techniques that are easy to parallelize. In this case, we did not parallelize it, but it could be. And linear or even sublinear on the number of edges, right, depending on the size of the data. So with that, I'd like to thank you for listening, and I'm happy to take any questions.